In this video, we're going to look at a little bit of motivation for section 14.7 by looking at a recollection of section 14.6, the linear and the quadratic approximation. Okay, so the linear and quadratic approximation are the important ground tools that you're going to need to transition into 14.7 really well. Okay, so recall the general setting here. We have maybe some function of two variables. Okay, let's say this has been given to you. Okay, you've got a given function, and we've got a given point P, which we'll call x naught, y naught, a given point of interest. Okay, and we know that there is the gradient of that function. So this is the equivalent of the first derivative. Yeah, so the first derivative of the function we know is the gradient. It's the partial derivative of the function with respect to x and y put into a vector, okay, called the gradient. We also know that there is a matrix called the Hessian of the function f, and it's the matrix that you create if you take the gradient of the partial derivative with respect to x and take the gradient of the partial with respect to y. And if you stack those on top of each other, you'll get the gradient of the first derivative fx would be fxx, fxy. So there is the gradient vector of fx, and then the gradient vector of fy is fyx, fyy. So here is the Hessian of the matrix. And this is the equivalent of the second derivative of a function. And the gradient is your first derivative. Okay, and now what we do with those first derivatives is we create the linear approximation. And we're going to create the linear approximation at the point x naught, y naught. So we need the function value at that point. You need the first derivative evaluated at that point. And then you need to do the dot product with x minus x naught, y minus y naught. So there is the linear approximation. Okay, so that is one place where the first derivative shows up. Okay, and then you'll also recall one other place, the gradient of the function at the point P shows up in one other place. Not just in the linear approximation tangent plane formula, but it also shows up in the tangent line problem. And the tangent line problem was a similar problem that if you had a function z is equal to f of xy, and you had a point given down here, x naught, y naught, and you had decided to choose a certain direction u could be a direction vector, that there would be a line that goes to that point, that vector u, or a line that contains that vector u as its direction vector. You could then create this curve on a surface, and at this same point right here, we could create something called the tangent line. And the equation of this tangent line is equal to L is a function of t. We're going to make a parametric function, so a line is a one-dimensional object. We're going to put the function at the point x naught, y naught. So that is the equivalent of our point P on the surface. Maybe let's call it Q. Here's our point Q on the surface, and here's the point P down in the xy plane. Plus, and we just need to add on the direction vector, which is u, whatever it was, that's going to take up two entries. And then the third entry, the z entry of the direction vector, it's going to be the gradient of the function at the point P dot producted with the vector u. And then we'll multiply by t. So essentially what we have is the directional derivative here. The directional derivative of the function is showing up in the z entry of the tangent line, telling you essentially how much your function is changing in the z direction as you move in the xy direction u. Okay, so that's the two places where the gradient shows up. One in terms of a tangent plane, a linear approximation, the tangent plane approximation of the function, which will actually be a plane. But then we also have the linear approximation called the tangent line. The next thing we needed was to move to the second derivative. Okay. And that's where we came up with this thing called the quadratic approximation. The quadratic approximation is the linear approximation, and then you need to just add on 1/2 the Hessian at the point P. So that's the equivalent of the second derivative. And then we need to multiply by x minus x naught, y minus y naught. And we need to do that again for the squared part of the quadratic approximation. And there is a video that you can watch on how to compute that. The thing that's going to be important for moving on to the Hessian and the second derivative test, which is what we're going to do in section 14.7, is I would like to talk about something called the directional, not the directional derivative, but maybe the directional second derivative. And that will be the key to the second derivative test. So before we move on to the directional second derivative, let's just look at a couple examples of just the linear and the quadratic approximation to make sure that we were on board with that idea. Here is a function of two variables, x and y, and the computations below, and we're going to pick the point x naught, y naught is 0, 1 in the xy plane. And so here we can see the computations that you should double check. Here's the function, the point, the function evaluated at x naught, y naught. Check that point out to get -10. Here is an example of your gradient vector. Here is your Hessian matrix. You should check those computations now. And what is really important is the gradient at the point and the Hessian at the point. You must evaluate the gradient and the Hessian at the particular point so that you don't have x's and y's floating around in your gradient or Hessian. You need to actually plug in the point of interest. And here is the linear approximation formula. Okay, you should try to compute this from the example from the computations above. And the answer you'll find will come out to be -7 minus 3y. And if you compute the quadratic approximation formula as we've written down and compute that as has been done in a previous video, you can see that you do get something with a quadratic term in it. Okay, you also have linear terms, right? So a quadratic approximation can be something, a function of x and y that has a total combined power of 2. Okay. So here the linear approximation, we're kind of familiar with this. It is just the tangent plane. Okay. There's the quadratic approximation, which now has a little bit of curve to it because it's bending a little bit like a quadratic function. Okay. And we know that if we were to zoom in just a little bit more on this thing, that we could probably make the function and the quadratic approximation kind of get a little bit closer to each other if you zoom in on it. Okay. So what we're seeing is the fact that the quadratic approximation, here's the red graph is the difference between those functions. So if you can see right here, right near this point of interest, 1, 0, the function and the quadratic approximation are almost the same, so the difference between them is 0. It's only when you move farther away from the point that you see the difference get bigger. Right? So that is the linear and quadratic approximation. Okay. The next thing I want to do is kind of hint at the directional second derivative. Okay. And I have a little example here. Second derivative test. I just want to look at a very particular. Okay. So here is a problem that we'll go through the steps now. I'll outline it here. And we can see that, again, we've got a function of two variables. In this case, a much simpler function, x squared minus y squared at the point x naught, y naught. We can compute the gradient, and you can compute the gradient at that point. Notice that the gradient at this particular point, 0, 0, is 0, 0. This is going to become important for us in the future. When the gradient evaluated a point is the 0 vector, that's called a critical point. And we've looked at the Hessian, and we've evaluated the Hessian at the point. Okay. Now, we're familiar with the idea of taking the gradient dot producting with the vector, okay, and to get the directional derivative, okay. And we know that somehow that this 0 shows up in the z entry of the direction vector for the tangent line, right? What we'd like to look at now is the test of the second derivative in a direction. Okay? So what we're going to find is that if we take our Hessian matrix and multiply it by the direction vector twice, we're going to get a number. And that number has a significance. It shows up in the z entry again. And we'll see what the significance of that second directional derivative is. In this case, it is 2. When you take the Hessian multiplied by the direction vector twice, that's the second directional derivative. Okay? And if we look at a plot here, we'll be able to see that what we're trying to do is to look at the function. Okay, I can show you what this function looks like. Our actual function, x squared minus y squared, looks like this. Okay. What we're interested in doing is checking the curve in any direction. So if you notice this, that if I look at change the direction, can you see that this curve is going to change? And sometimes the curve bends up like a parabola, sometimes the curve bends down like a parabola, right? So in different directions, the curve changes differently. And we'd like to figure out whether or not that curve is acting like a parabola, pointing up or pointing down. And that's what the second directional derivative is going to show us. Okay, so let me just switch back to my screen here, and we can do a quick second directional derivative. Okay. So in the function we just did, it was the function f of xy was x squared minus y squared. And here we're trying to motivate the second directional derivative. Okay. We know that the gradient is 2x comma 2y, and the Hessian is the gradient of 2x stacked on top of the gradient of 2y. The gradient of 2x is equal to 2. The partial derivative with respect of 2x with respect to x is 2. Partial with respect to y is 0. Partial with respect to x, partial with respect to y. So here's our Hessian. Okay. Now if you pick a particular point, x naught, y naught, let's say that we pick the point 0, 0. Okay. And we pick the direction vector v to be 1, 0. We just chose this, just chosen at random. You'll notice that it happens to be the x direction. So what we're trying to do here is create a curve on the surface in that direction, v. Okay, and we'll just compute the second directional derivative, which will be the Hessian at the point P, multiplied by the vector v, multiplied by the vector v. So 2, 0, 0, 2, multiplied by the vector v, multiplied by the vector v. And we know the way to compute from previous videos, the way to compute this multiplication is to look at the first vector of the Hessian and then dot product it with 1, 0. And you will get 2, 0 dot producted with 1, 0 is 2. Take 0, 2 now and dot product it with 1, 0, and you get 0. That's the first multiplication. And now you have a third dot product to do. 2, 0 multiplied by 1, 0 as a dot product will give you 2. So what we're seeing here is that this is in fact 2, but more importantly that it is a positive number. Okay, and what we know then is that this function, this one's kind of, saddle points are always kind of hard to draw. I'll try to draw it this way. What this function looks like at the point 0, 0, and let's make this our x direction. In the x direction 1, 0, we know that that function is going to look like a parabola, and that parabola is going to open upward because we have a positive number. Okay, so that's just a little hint at how we're going to compute, figure out what the function looks like in a particular direction using the, does it curve up or down like a parabola, and we're going to use the second directional derivative to do that. More in later videos.